this video, we'll explain how to find the area between two curves using integrals. Let's look at this example. We want to find the area between the curve y is equal to 1 minus x squared and y is equal to x squared between the vertical lines x is equal to minus 1 over square root of 2 and x is equal to 1 on square root of 2. The first thing we're going to do is sketch those curves to see what exactly we're trying to calculate. We recognize that these curves are both parabola, one of them opening up and the other one opening down. The parabola y equal to x squared go through the points with coordinates 1, 1 and negative 1, negative 1. The graph y equal to 1 minus x squared is a parabola opening down. Its x-intercepts are negative 1 and 1. The x-coordinate of the vertex is given by minus b over 2a. And of course, since b is 0, there's no coefficient with x. It corresponds to 0. So this is what it looks like. We notice the points of intersection here. Let's find out what they are. The coordinates of these points of intersection are the solution of this system of equation. To find the x-coordinate, we can just say that y is equal to y, basically. So we get 2x squared equal to 1, x squared is equal to 1/2, and as a result, x is equal to plus or minus 1 on square root of 2. So this point of intersection here, so that's 1 on square root of 2, and this other one is minus 1 on square root of 2. Therefore, the area we're trying to calculate is this area there in between the two curves. The problem we have is that so far, if we use the integral, we know that if f is some positive function, so that's y equal to f of x, and we have two numbers a and b, we know how to calculate the area as an integral, but that only works if it's the area between the graph of f and the x-axis. But that's something that could be useful here, because we could get this area by subtracting. If we calculate this blue area, all of that, and if we then subtract the area under the second parabola represented in green, what we will get will indeed be the area between the two curves. Let's do that. So the area we want is basically the blue area minus the green area. And each of those can be calculated this way, calculating the integral of a positive function between two values. So let's do this. My blue area is the integral between minus 1 on square root of 2 and 1 on square root of 2 of the graph at the top, which is y is equal to 1 minus x squared, minus the green area, which is the area under the graph of y equal to x squared. If you notice that both functions are even, so this is an axis of symmetry, a better way of calculating the blue area would be to calculate this area on the right of the y-axis and multiply by 2. Same thing for the green one. Now, what we're going to use is a property of integrals. Please note that we have the same endpoint. So if you have the same endpoint and you're adding or subtracting integrals, we can just add or subtract the functions inside. So we get 1, and here minus x squared, so that's minus 2x squared dx. I'm assuming that most of you wouldn't have noticed the symmetry, so I'm just keeping the initial endpoints. Now we need an antiderivative for the function inside the integral, so we get x minus 2 times an antiderivative of x squared, and that's going to be x cubed on 3 between 1 on square root of 2 and minus 1 on square root of 2, between minus 1 on square root of 2 and 1 on square root of 2. And now we just sub in. So we get this 2/3 1 on square root of 2 cubed. That's my f of b, if you'd like. And now same thing with minus 1 on square root of 2. If I combine those two, I'm going to get 2 on square root of 2. And if I combine these, when I cube a minus sign, I still have a minus sign. So I'm going to have a minus here, and another minus, so that's minus. So if I combine all of those, I'm going to get minus 4/3, 1 on square root of 2 cubed. I'm running out of space. Let me restart up here. So when I cube square root of 2 here, I'm going to use 2 of the square roots of 2 to create a 2, and I'm going to keep the other square root of 2. Once I do this, I can see that here I get a cancellation with a 2 at the top. The denominator of this fraction is now 3 times square root of 2. So what I'm going to do is multiply the top and the bottom of that one by 3. So my denominators are now equal. So what I get is 6 on 3 square root of 2 minus 2 on 3 square root of 2, and that's 4 on 3 square root of 2. If we decide that we don't want square root of 2's at the bottom, we can rationalize and multiply the top and the bottom by square root of 2. In that case, we get 4 square root of 2 at the top, and at the bottom we get 3 times 2, so we can cancel again, and we get 2 times square root of 2 over 3. Let's try another example. We want to find the area bounded by the x-axis and this curve between x equal to -2 and x equal to 2. Maybe the first idea that comes to your mind is to calculate the integral of this function between -2 and 2. But beware, that may not be equal to the area. Indeed, you need to remember that if an area is above the x-axis, let's say that's 3, it's going to be counted positively in the integral, but if it's below the x-axis, it's going to be counted negatively. For example, if this is a and this is b, the integral of the function f between a and b wouldn't be 5. It would be 3 plus minus 2. So really, the integral would be 1. So beware, what the integral calculates, it's not the area, it's the signed area. There is a sign, which is plus if it's above and minus if it's below. So we actually can't do that, and we need to know what the graph looks like before we can do the calculation. Let's sketch it. It's a cubic, and the x-intercepts are 0, 2, and -1. The limit as x approaches plus infinity is plus infinity. And that's enough to know what shape we get. We're going to get something like that. The question says that we want to find the area between x equal to -2 and x equal to 2. So that's my -2. So the area we are trying to find is the sum of that first area, this second one, and that third one. And let's call them A1, A2, A3. As mentioned earlier, if we just calculate the integral between -2 and 2, what we will get will be minus A1 plus A2 minus A3. So what we're going to do is calculate these three areas separately and add them. So let's calculate A1. When we calculate the integral of the function between -2 and -1, what we get is negative. It's the opposite of A1. So in order to get A1, we could just put a negative sign in front of the integral, and that would make it positive. Okay, let's calculate this integral. So we need to find an antiderivative of the function. And we realize that finding an antiderivative of a product is much harder than finding an antiderivative of a sum. So it would be a really good idea in that case to expand before we actually find the antiderivative. Let's do that. So y is equal to x, and if I expand those two, I get an x squared. How many x's do I get? When I distribute, I get minus 2x plus 1x, so that's minus x. And finally, the constants, I multiply those two and get a -2. Now I can distribute this x, and I'm going to get x cubed minus x squared minus 2x. So we can now use this expression for our function. And we can put this negative sign inside the integral and distribute it. What we will get is the following. Minus x cubed plus x squared plus 2x dx. Notice that when you distribute a negative sign, all the signs change. From there, we follow our usual procedure of finding an antiderivative for each term of the sum. Keeping track of the endpoints. And then we sub in the endpoints. You will have to be careful with the signs when you do so. You will have to be careful with the signs when you do so. When you raise a negative sign to the power of 4, you get a plus. And when you raise a negative sign to an odd power, you get a minus. When you raise a negative 1 to a power of 4, or more generally to an even power, you get a plus. When you raise a negative 1 to a power of 3, or more generally an odd power, you will get a minus. Now you sub in negative 2. So you're going to get a 16 on 4 minus 8 on 3 plus 4. And you simplify all of that. This is minus 4 here. It cancels with this plus 4. And we can use a denominator of 12 for all of these terms. So we're going to get a minus 3 from this one. This one we need to multiply top and bottom by 4. We get a minus 4. We get a minus 4 plus 12. And then here we have a minus and a minus together, so that's plus 8 on 3, which we need to multiply by 4 at the top and the bottom to get a denominator of 12. So that's plus 32. And our final result is 37 on 12 for this first area. Please note that putting the negative sign at the front has done its job. We're getting something positive. That's actually A1. Let's now calculate A2. Since the graph of f is above the x-axis, the integral of f between -1 and 0 is actually A2. We find an antiderivative in which we sub in the endpoints. So when we sub in 0, we obviously get 0. When we sub in 1, we get a quarter plus a third minus 1. The common denominator of all of those will be 12. So we're going to get minus 3 minus 4 plus 12. And this simplifies to 5 on 12. So A2 is 5 on 12. Let's now calculate A3. The area we want is below the x-axis. So what the integral will calculate is not the area, it's its opposite. We're going to get something negative. So what we're going to do to fix this, exactly like for A1, we're going to put a negative sign in front of it. From there, it will be really similar to A1. Remember how we distributed the negative sign to get there? And then we found an antiderivative. We can really copy those results. We just need to change the endpoints. And now we sub in the values of our endpoints. We notice that the -4 and the 4 cancel, so the area A3 is equal to 8 on 3. The area we are after is the area bounded by the x-axis and the curve, so what we want is the sum of these three areas. We just need to add the results we have. That's 37 over 12 plus 5 over 12 plus 8 thirds. And using same denominators, this will simplify to 37 over 6. Note that we could have used Maple to do all of this or to check our work. So A1 is this area here. Maple can calculate the integral, and since it would be counted negative, we put a negative sign in front of it. That's exactly what we did by hand. A2 is this area there. The integral is exactly the area. A3 is this area. It's below the x-axis, so we need to compensate. The integral is the opposite of the area, and then we add them. See, the code is pretty easy, so feel free to use Maple when you want to check your results. Let's summarize how to find the area between two curves. So let's say that what we want is to find this pink area. It's really the sum of these two areas, which I could call A1 and A2. The way to calculate A1 and A2 will be slightly different. To calculate A1, we would calculate this blue area, and then we would subtract. And then we would subtract this green one. In order to do this, what we would do is integral of f of x minus g of x between a and b. Now, in order to calculate a2, what we would do is find this area under the top curve and subtract the area below the other curve. That one. So in that case, your expression would be slightly different because you would do the area of g minus the area of f. Right, so you realize that when f is above g, what you want to integrate is f minus g, whereas when g is above f, what you integrate is g minus f. So basically, the one above minus the one below, the one above minus the one below. And that tells you how you're going to deal with these questions in practice. You will need to sketch the graph, otherwise there's no way you're going to know which one is above the other one. You will need to find the points of intersection, so in that case you would have this, because that's going to tell you how to split your interval of integration. You will split your interval of integration into sub-interval, making sure that on a given sub-interval, f is always above, so that's on AB for instance, or g is always above. And then on each sub-interval, you integrate the function curve above minus curve below. That's what we did. We got A1 and A2, and then you sum those. There is a very elegant formula that summarizes these ideas. It says that the area between the graph of f and g can be obtained by integrating the absolute value of f minus g. Let's see why this works. Well, either f is above g or vice versa. So let's first deal with the case when f is above g. That means that f of x is going to be greater than or equal to g of x. So if you subtract g of x from both sides, that means that f of x minus g of x is non-negative. So if you take the absolute value of a non-negative number, you get the number itself. So what we see here is that if we integrate the absolute value of f of x minus g of x on an interval where f is above, really we are integrating f of x minus g of x. That's exactly what we wanted. Let's now assume that f is below g. That means that f of x is less than or equal to g of x, and if we subtract g of x from both sides, same thing, we get the fact that this is a negative number or equal to 0. Therefore, if you take the absolute value of this number, which is negative or equal to 0, you will get its opposite. When you want to take the absolute value of a negative number, you just need to put a negative sign in front of it. Now what we can do is distribute this negative sign, and what we will get is minus f of x plus g of x. In other words, g of x minus f of x. That means that if we integrate absolute value of f of x minus g of x on an integral where f is below g, we're really integrating g of x minus f of x. That's exactly what we wanted. In other words, this absolute value will be sometimes equal to f of x minus g of x. That's exactly if f is above. And sometimes it will be equal to g of x minus f of x. And that's going to happen if g is the one above and f is the one below. Please note that the idea of splitting the interval of integration into sub-interval where it's always the same function above and the same function below is exactly what we've done when we calculated this. in case you're wondering, but there's only one function here. No, really there are two. So one of them is f, that's the obvious one, and the other one is the x-axis, which is the graph of the function y equal to 0. When we calculated the first area A1, we did the function at the top, 0, minus the function at the bottom, which is f, between -2 and 1. So really the integral of minus f dx, or if you'd like, minus the integral of f of x dx. Then when we calculated A2, we did the integral between -1 and 0 of the function at the top, that's f, minus the function at the bottom, and that's 0. So really the integral of f between -1 and 0. When we calculated A3, that's the integral between 0 and 2 of the function at the top, which is 0, minus the function at the bottom, which is f, which is why we're getting the integral between 0 and 2 of minus f of x dx, which is the same as what we get if we put the minus sign on the outside. Everything is consistent. That's math. Thank you for watching this video.